Extreme weather and climate events are increasing in frequency, intensity, and duration. These events pose huge challenges to society, ecosystems, and economy. Traditional modelling methods have limits. They often treat extremes simply as tables of distributions and may struggle with complex interactions, changing baselines, or multidimensional dependencies. So, where does artificial intelligence come in?
AI is transforming the way we detect, model, and understand extreme weather. By leveraging vast amounts of data from satellite imagery to climate simulations, we are now able to advance beyond the standard questions of the what, when, or where these events happen to more interesting ones, like understanding the why and also gaining some confidence on the predictions of the models.
However, harnessing AI in this domain comes with important methodological and operational considerations. We highlight three major categories of challenges: data, model, and integration.
We have two main hurdles here. The first one has to do with the data gap. When it comes to data, of course, we have vast amounts of data, but the reality is that we have very few labeled data to learn from. The second one, the definition of an extreme event. We know that extreme events are by nature very rare, and when it comes to a statistical definition, they live on the tails of a very high-dimensional, very complicated data distributions. And that, in turn, makes these models to be not relatively accurate when it comes to extrapolation or generalization outside the historical record that we are learning from.
To ground this in concrete examples, we focus on four major hazard types. For droughts, AI can integrate satellite imagery, soil moisture, vegetation indices, climate predictors to improve detection and forecasting of severe multi-year events. For heatwaves, AI models are helping learn patterns, drivers, and enable attribution, for example, separating thermodynamical versus circulation drivers. For wildfires, which often stem from complex drivers and feedbacks, AI can assist in risk mapping and understanding pyrocumulonimbus formation, risk assessment, and how they spread. For floods, AI is used not only to model hydrology, but also to communicate risk using 3D visualizations and personalized messaging for better early warning systems. So, what are the big takeaways?
To move forward, we need to develop the new generation of trustworthy AI algorithms. Algorithms and models that are not only accurate, but also they are more robust to data distribution shifts, as well as more interpretable and accountable. We advocate for hybrid models, models that can incorporate physical laws and domain knowledge to constrain the space of solutions of these algorithms. This way, we will account better for uncertainties and quantify better the extreme event weather regimes.
In short, AI isn't magic, but it's a powerful tool for climate risk and disaster management. So, what's next?
Real impact happens when we can bridge the gap between AI and climate sciences. But not only those two sciences, but also social sciences and behavioral psychology are involved here. Only when we gain trust on these models, not only us, but also stakeholders and policymakers, we will be able to advance a more robust, trustworthy, and operationalization of these algorithms and models into early warning systems that can save lives.
Read the full paper if you'd like more details.